So, hi again. This will be the last lecture on the board in this unit. During the last video, we have derived, or we have seen that there is an equation that relates the applied external voltage to the current flow across such a semiconductor electrolyte junction. And in the last video I said that we will discuss this in this video. We will do this, but prior to this I would like to introduce a concept or a phenomenon at this junction that is also very important. Personally, I would like to mention it. So now let's have a start at this. This energetic situation at the semiconductor electrolyte interface is established because the electrochemical potential of the electron prior to contact formation was lower compared to the semiconductor. Therefore, from an energetic point of view, it was favorable that electrons leave the semiconductor during the formation of equilibrium. And this means in turn that here at the phase border you have negative charge, a thin layer of negative charge. Electrons that left the semiconductor during the formation of equilibrium because energetically it is favorable. However, because the density of states in the semiconductor is low, you have here the formation of positive charge. And people call this the depletion layer W because it is depleted of majority carriers, or the free carriers, the electrons in the semiconductor. This region of the semiconductor is depleted of electrons, therefore it is called a depletion layer. However, you have here positive charge. So this area is positively charged. And compared to a metal, this layer is thick because the density of states is low compared to a metal. If this would have been a metal, you would have ended up in a different equation for the current voltage relationship as we have derived in the last video, just to mention it. So this means that the semiconductor has unique properties and does not act like a metal because its density of states for electrons is low compared to a metal. And we have arrived here at this situation again because of the positions of the electrochemical potentials of the electrons before the contact formation. But however, what would have happened if mu tilde would be higher than in the semiconductor before the formation of the equilibrium, before one soaks the semiconductor electrode into the solution, or into the electrolyte solution, then electrons would have been transferred to the semiconductor, specifically to the valence band, to empty states in the valence band of the semiconductor. And then you would not have a depletion layer, you would have just a thin region here. If you think in spatial coordinates, or if you think spatially, a thin layer of negative charge in the semiconductor. But this would eventually mean that you do not have a current voltage characteristic as we have derived in the last section, but this junction would behave similar to an ohmic contact. This is the case called the case of accumulation, because the negative charge would accumulate here instead of the formation of a depletion layer. And this case is called the case of depletion. However, this will be also interesting in the next video, therefore I covered it here for your understanding, and I also think it's important to mention. However, let's continue now with what we have had in the last video. We had derived current voltage relationship at such junction. And we have found an equation. So the current I is related to negative I0, which is a constant factor. And in the brackets we have this exponential term, elementary charge, externally applied bias, Boltzmann's constant, temperature -1. So a good idea now is to plot this equation or this graph. So here let's draw an axis, a current axis, and voltage axis. So now let's consider the cases. If V is 0, this guy becomes 1, this 0, which is kind of logical because if you do apply an external current on external voltage, why should there be a current flow? If this guy here, if the voltage becomes negative, the exponential becomes positive, increases, and you have an exponential branch in this direction. Physically, how to interpret this? So now let's have a look at this diagram here as well. If I apply a negative potential here, then I force, let's say, electrons to travel in this direction. And that means I inject electrons into the depletion layer. The depletion layer becomes thinner and the electron transport is enhanced. And people often call this negative current, or in electrochemistry it's often called cathodic current. However, if I go into the other direction, then V becomes positive, this exponential goes to 0, and basically on the other side I have a curve that flattens out or approaches the limit. So, but no exponential increase of the current. So it's also clear, or by looking at this diagram, this would mean, okay, I try to remove electrons now from the depletion zone. The depletion zone becomes even more depleted and its width increases, and therefore you have kind of rectifying behavior or stop behavior, and the current cannot increase, or you have just very low current flow. Also, this is called the dark current mode. Also, if you look at this, I've talked about this is similar to a diode. Of course it is, but why does it look not different? I think this is just due to notation, because the electronics guys, they often consider the flow of positive current particles. The electrochemists consider negative electrons in their notation, and they also have a different notation what is negative and what is positive bias. Therefore, this curve is inverted twice. It's inverted on the I-axis and inverted on the V-axis, but it's just notation. Do not just think of it as a diode. So next thing I said, or the next good question is, because our topic was the semiconductor photoelectrochemistry, or yeah, should be, because the formation of the polysilicon colloid is such a process. Now we ask ourselves the question, what happens when you irradiate such a junction with light, and in particular light, or with photons having energy higher or bigger than the band gap. The band gap is the difference between the valence band and the conduction band. However, by doing so, one can excite an electron from the valence band to the conduction band, and then here an electron hole is generated and a free electron here is generated. And we will do it in the depletion layer. But in the depletion layer, there is an electric field, and this electric field accelerates the holes, the electron holes, to the semiconductor electrode interface, and the electron is accelerated towards the bulk. So if here is now an electrode and here is an electrode, the charges are separated, and one in reality measures the net current. Because the driving force is the separation of a charge carrier pair that is generated with light, and the built-in voltage separates the two charges. And if you have electrodes here, contact here and here, then you can remove or separate the charge pair, which is basically the principle also of a solar cell. However, for this equation, this means that if you have a zero voltage, at a zero voltage you measure already a current. And from a mathematical point of view, this is just an offset of this equation. And let me draw it here. Just add a constant current. Here in the graph, and here one just adds a constant I photo, which is the photocurrent. Basically, we are already very far. We can recap a bit. One thing I forgot, that this branch here is often called the anodic current by the semiconductor photochemists. And yeah, we are almost complete now. One thing is very interesting, that the steepness of this curve here, I forgot, can be adjusted by the shifting of the Fermi level here in the solution side, and the Fermi level can be adjusted by just pouring in the liquids or changing the composition of the electrolyte solution, which is very present if you think about it, because let's say if this were a metal, you would end up in the same current voltage characteristic, but tuning the steepness here would be more difficult, because you would have to change the composition of the metallic contact. In the solution, this is easier, but the drawback, if you would like to utilize this in an electronic device, the charge transfer, the very nature of the charge transfer between the electrolyte and the semiconductor has a lower efficiency than the transfer rate when you consider a semiconductor and a metal. Okay, just this. And at the end of this sub-lecture, just for completeness, I would like to write down the main ingredients for the occurrence of this photocurrent. So just to write it down, so the effect of illumination of the contact. What happens? So we have an electric field in the depletion layer. And the incoming light, photons having an energy bigger than the band gap, create an electron hole pair generated by h bar omega, and the electron is accelerated towards the bulk, and the hole is accelerated towards the interface. So this very interesting. People have even considered, or people even build solar cell with this approach. So this is not part of the lecture. I think it's not on the exam, but if you're curious, very famous solar cell built with such approach is the Gratzel cell. Maybe if you're curious, you can Google it. Just for completeness, I personally think this is interesting stuff. Maybe you think so as well. And now this is also already the end of our last board lecture. Hopefully I've covered everything completely and made no mistakes. Otherwise I will inform you. Hope it was also enjoyable for you. And the next lecture will be a PowerPoint lecture. I will present stuff about the porous silicon carbide that we prepare here, and also some possible application scenarios for this material. Yeah, and see you in the next lecture, and yeah, thank you for the attention.